So we'll continue today working on chapter 6. So we have covered last time how to find the roughness of a surface by calculation. Okay. And now we will talk about the surface integrity. We know that the surface texture alone does not completely describe a surface. There may be metallurgical changes in the altered layer beneath the surface that can have a significant effect on a material's mechanical properties. So, surface integrity is the study and control of this subsurface layer and the changes in it that occur during processing, which may influence the performance of the finished part or product. So roughness or surface, when we talk about surface texture, we are just considered with the geometry of the surface. So we look at the outer layer of the surface, okay, just here. But when we talk about surface integrity, we go beyond this limiting zone, and we go deep into the material, and we see what are the properties in this layer, which is beneath the surface. Okay. Now, concerning surface changes caused by processing, we can have a variety of surface changes that are caused by the application of a variable form of energy during processing. For example, one of the possible alteration of the surface sublayer and which will affect its integrity is the use of mechanical energy, which is the most common form in manufacturing. So, for example, processes as forging, extrusion, and machining will affect this layer surface properties. Now, although the primary function is to change the geometry of the work part, sometimes mechanical energy can also cause residual stresses or work hardening or cracks in the surface layers. And all of these issues will affect the integrity of the surface because they will change the characteristics of this sublayer beneath the surface. Now, we have several energy forms that can affect the surface integrity. So we have seen already mechanical energy that can cause, for example, a strain hardening of the material or can cause residual stress or cracks formation. Okay. Other types include also thermal energy, which can cause metallurgical changes. And in the case, for example, this is the case of recrystallization. We have seen together that if we heat a certain material up to its recrystallization temperature, we have formation of new grains. So we have new characteristics of the surface sublayer. It can also, for example, another thermal energy alteration is the formation of a heat affected zone, which is a non-melted area of metal that has undergone changes in material properties as a result of being exposed to high temperatures. This is, for example, the case in welding or if you have a high heat cutting operation. Okay. Another type of energy that can alter or affect the surface integrity is the chemical energy. Chemical energy can lead to corrosion or to contamination of the surface. We have also the etching process, which is a traditional process using strong acid or mordant to cut certain parts of the material, and this will create a designed incised metal. Other form of energy is the electrical energy, which can cause change in conductivity or magnetism property of the material. So all of these energy forms can affect the surface integrity of the material. Now, what about measurement of surfaces? So we have two parameters of interest: the surface texture, which is just considers the geometry of the surface, so the external profile of the surface, and it is commonly measured as surface roughness. The other parameter of interest is the surface integrity, which will deals with the material characteristics immediately beneath the surface and the changes to this subsurface that will result from the processes creating it. Now, concerning measurement of surface roughness, we have several methods to measure surface roughness. We have first subjective comparison with standard test surfaces. So this will, for example, this is the case of fingernail test, but it is a very subjective comparison, yani, because you just rely on touching the surfaces and compare their roughness. Of course, it's not a very accurate method. A second method is the stylus electronic instruments, and we will see it in detail in following slides. And we have also optical techniques that can be used. First, what about subjective comparison? It consists on comparing the roughness with a set of surfaces of known roughness. So if you have several surfaces with known roughness, and by touching them, you compare the touch of these surfaces to the actual surface. When you see that it's nearly the same, you can say that I have comparable the same roughness. But of course, this is not it's not an accurate method, and as we go into smaller roughness, it will not work anymore. Okay, and we need more sophisticated tools to use. Yes, this is the fingernail test, this method. Okay, now second method is using stylus instruments, which is similar to the fingernail test, but it's more scientific because in this case, we have electronic devices, as for example, a cone-shaped diamond stylus, which will traverse across the test surface at low speed. And as the stylus head is traversed horizontally, it also moves vertically to follow the surface deviation. We will see the setup now together. The vertical motion is converted then into an electronic signal that can be displayed as a profile of the actual surface or an average roughness value. So let us see together the setup here. So this is a figure of the setup showing stylus instrument which will traverse a standard test surface. So this is in live a picture of it. You can see it here with the different details. So what is happening is that this is your material and you need to measure the surface roughness. So what you do is you move your stylus along the horizontal direction. And as you move it, you have the head of the stylus which will move vertically following the deviations in the surface. And this vertical motion, okay, will be recorded to show you how the roughness of what is the roughness of your surface, because the vertical displacement will allow you to determine the roughness. If you don't have vertical motion, this means that you have a surface that is perfectly smooth. So imagine that you have a surface that is perfectly smooth. As long as you move in the horizontal direction, you will not have vertical motion of your stylus head. Okay, so it will give you zero displacement. However, if you have variation in roughness, then your stylus will move vertically as you are moving in the horizontal direction, and this motion can be transformed to an electrical signal that can uh, give you what is the value of the roughness. Now, other optical techniques is the use of microscope. So we can use a microscope with a digital camera and a motorized table, which will allow us also to see our surface. Okay, we can see it. So it will give us a 3D view of the surface, which will allow us to determine its characteristics. Now, concerning tolerances and manufacturing processes, we have already seen that each process will have a certain tolerance. And of course, some manufacturing processes are inherently more accurate than others. Most machining processes are quite accurate, capable of tolerances up to plus or minus 0.05 millimeter or better. Another process that is not very accurate is sand casting. So in general, sand casting is less accurate than other machining processes. and it can have tolerances of 10 to 20 times more than machined parts. But of course, when doing any manufacturing process, we should know before what is the tolerance of the process, and depending on our uh, the final desired product, we can determine if it's acceptable for us or not. Now, finally, for surface and manufacturing processes, as we have seen that not all processes will produce the same accuracy, okay? And in general, processing cost will increase with the improvement in surface finish because additional operations and more time will be required to obtain increasingly better surface. So, and also we have processes that will enhance the finishing of our object. So processes noted for providing superior finishes are include honing, lapping, polishing, and super finishing. And these processes will come after other processes. And sometimes in machining operations, even if they are accurate, if you need a very high accuracy, you need perfectly smooth surface, you need after machining to do other processes that will smooth more your surface. For example, in the videos you watched, you have several examples of finishing processes. For example, honing will use a special tool called a honing stone or a hone to achieve a precision surface. The hone is composed of abrasive grains that are bound together with an adhesive. In general, honing grains are irregularly shaped, and smaller the grain sizes, then smoother will be the surface of the final product. Concerning lapping, lapping is a machining process in which two surfaces are rubbed together with an abrasive between them, and this can be done by hand movement or using a machine. For polishing, polishing is the process of creating a smooth and shiny surface by rubbing it or by using a chemical action, leaving a surface with a significant specular reflection. Concerning super finishing, which is also known as micro machining or micro finishing, it is a metalworking process that improves the surface finish and workpiece geometry. This is achieved by removing just the thin amorphous surface layer left by the last process with an abrasive stone or tape. This layer is usually about 1 micron in magnitude. So super finishing is one of the most accurate processes that will give you a nearly perfectly smooth surface. Any question on this? Okay. Now we will see together some examples on in the videos you have seen. They explain for you how to read vernier calipers and how to read micrometers. And I will do some practice with you today, and we will go over some examples. So, first, the first type, okay, is the of vernier scale is the linear one, okay, and in this case, the precision of length measurements may be increased by using a device that uses a sliding vernier scale. In such instruments that are based on a vernier scale, which you will use in the lab to measure lengths of objects, we have the vernier calipers and the micrometer screw gauge. First, we will start with reading of vernier caliper. These instruments have a main scale in millimeters and a sliding or rotating vernier scale. Okay, so we will see together both cases, the sliding scale and the rotating scale. In the figure below, for example, we can see the sliding scale. Now, for the sliding scale, it can be divided into a certain number of divisions. And higher is the number of division, higher will be the accuracy of the reading. So for example, here, if you look at this figure, this is the main scale. This is your main scale here, okay? And this is the vernier scale. Your vernier scale here is divided into 10 parts, okay? So, and each, you know that the total, the total value is 0.1 millimeter since the main scale division is 1 millimeter. Okay, uh, so now the vernier scale will divide the 1 millimeter. So if you have 10 division, for example, then you are dividing the 1 millimeter of the main scale into 10 parts. So your vernier scale will be 1 over 10, which is 0.1 millimeter. If you have, on the other hand, for example, instead of 10 divisions, 100 divisions, this means that in your vernier scale, you are able to read 1 over 100 millimeter. Okay? Now, what is the technique how to read such a scale? So the main scale reading is the first reading on the which is immediately to the left of the zero of the vernier scale. So look at this figure, for example. I look at the zero of the vernier scale. Zero of the vernier scale is here. Okay, so it's between 3 millimeter and 4 millimeter. So I consider then that my first reading will be the one to the left of 0, which is 3. So I have first 3 millimeters. Now, to continue with my readings, I am between 3 and 4 millimeters. Okay, so now it is 3 point something. So to know what is the second number, I should look at the perfect match between any of my division and the main scale. What do we mean by perfect match? And they should be aligned. So here, for example, this line is in between of these two. Okay, this line also is not in match with any of these two lines. If you go, this is not, this is not, this is not. Here it is close, but not yet. Yani it's little bit. We have a small difference in between. So we are now getting close. Here you have the perfect match, which correspond to number 7. Okay, so from the vernier scale, the perfect match is at number 7, which correspond to 7 times 0.1, which is 0.7 millimeters. So in this case, you say that my final reading will be 3.7 millimeters. Okay, another example. Let us see here, for example, uh, how to read this value. So here it's little bit more complicated because here the vernier scale is divided into a higher number of divisions. Okay, so look, and how you know, all you have to do is to say, I am dividing 1 millimeter. Okay, I am dividing 1 millimeter into how many divisions? Here I have from I have count. So first I have 10 divisions. Okay, and even yani, each division is divided into 5. So if you want, this represents 0.1 millimeter, but each 0.1 millimeter is divided into 5 parts. So each part will be 0.02 millimeter. Okay, so here you are able to divide, to read up to 0.02. Okay, so this is your accuracy here. Okay, so in this case you are dividing even the number of division you have. Okay, is 10 times 5. You are dividing into 50 divisions. So 1 millimeter over 50 will give you that each part will be able to read 0.02 millimeter. So this is the degree of accuracy of your scale. Now, in order, the technique is the same. First, I look at the 0. Okay, this is my 0. Okay, I have first here, this is 3 centimeters. 1, 2, 3, 4, 5, 6, 7. So I have 3.7 centimeters, which is 37 millimeter. So until here, I have from the main scale. From the main scale, my reading is 37 millimeters. Now, in the vernier scale, I should look at the perfect match. Here, maybe because it's you have a lot of division, what they did for you, they enlarged the scale so that it becomes clearer. You should try to look at the perfect match. The perfect match is nearly here. I know it's a little bit it's not very clear, but of course in the exam the perfect match will be clear. Yani, you will see that here I have perfect match before and after. It's not a perfect match. Okay, so now if I consider this is the perfect match line, I have this correspond to, I have 4. Okay, so 0 point, this is 0 0.4, 0 0.42, 0 0.44, 0 0.46. Okay, so it's after the comma it's 46. So I can read 37.46 millimeters. Okay, is this is clear? Any question on how we read this? Okay. Another example. For example, here, if I consider the following figure, I look first at my 0. This is my 0. Okay. I have here 3 centimeter, 0.1234. So it's 3.4 centimeter or 34 millimeter. So from here, from the main scale, I read 34 millimeters. Then in the vernier scale, I will try to see the perfect match. Here you have a zoom. In the zoom section, you can see here it's really difficult to see the perfect match, and its difference is really small. But nearly you can see here that you have a small difference here and you have a small difference here. The perfect match is just at 6. So your reading is 34.6 millimeters. Okay, so this is the way we read linear vernier scales. We'll see also a practice. We'll have a practice uh, on rotation vernier scale. Okay, so here, what is the technique in rotation vernier scale? The first significant figure will be taken from the last graduation, shown on the sleeve directly to the left of the revolving symbol. Note that an additional half-scale division must be included if the mark below the main scale is visible between the symbol and the main scale division of the sleeve. The remaining 2 significant figures, which correspond to hundredths of a millimeter, are taken directly from the symbol opposite the main scale. So I will explain this here in detail. So this is another scale. Instead of having a linear scale, we can have a rotary scale. So in this case, how we read the values? First, for the main scale, okay, this is your main scale. And here you will have a notation to tell you that this will read millimeters. Okay, so in the main scale, first you look at the final graduation just before when you reach your symbol. Okay, so here you have 5 millimeter, you have 6, 7. Okay, so to the left of the symbol you can read the graduation which corresponds to 7 millimeter. Now after 7 point what, to determine point what, then you should look at the vernier scale. Okay, and you should look at the perfect match between this line and the vernier scale. This line is matching with this one. Okay, this one corresponds to, this is 35, 36, 37, 38. So your reading here is 7.38 millimeters. Okay, so this is how you can read it here. Now what you can see here, why we have your rotary scale is divided into 50 divisions, not 100. You know why? Because here what is happening is that you have your grading is, you can read here not only 1 millimeter, you can read 0.5. Okay, so you have the main notation if you want here, but these two, this is 0, this is 1 millimeter, but you have the one in between, this will read 0.5, 0.5 millimeter. Okay, so we will see an example that if we have, for example, the 0, if you have here this graduation, for example, if the symbol is here, then you will read 0.5 something. So you will add to 0.5 a certain number. This is why the rotary scale is the total, and if you do a complete rotation, you go over 0.5 millimeter, okay? Because you have this division. So for example, if you look at the following other example, yes, if you look here, okay, what will be your reading? First, you have, this is your symbol just here. So the division which is just before the symbol is this one, which correspond to what? So I have 5, 6, 7, and 7.5 here. Okay, so I should add to 7.5 what I read from the vernier scale. From the vernier scale, the perfect match is at this location here. So it is 20, 21, 22, it's 0.22. So I should add to 7.5, I should add plus 0.22. So I will get as a final reading 7.72. Okay, is this clear? Any question? Okay. Another example. So here in this figure, this is in the main scale. What do we read? We have 1, 2, 3. Look here, it is, يعني, we didn't pass yet the whole line. يعني. You can see that you will be very close to 3.5, but you didn't pass it yet. So it is 3 point, and what you can see here is you will see 46. So 3.46. This is why your symbol is very close to pass this, the 0.5 line. Okay. So here you can know from your second reading that you didn't pass it yet because you are on 46. Okay. So it's 3.46 millimeter. Now we'll give another example where you just pass it. So here you have just passed the 0.5 line. So, and this is clear from your reading here because it's the perfect match correspond to 6. So your reading will be 1, 2, 3, 3.5 plus 0.06, so 3.56. Okay, so this is 3.56 millimeter. Okay. Any question on readings of linear or rotary scales? Okay, so we can start to correct problems on chapter 6. This document, I will post it on Blackboard, okay? It's not posted yet. I will post it today, okay? So now, let me open the problems and start to correct them. Sorry, it's chapter 3. Okay. I will not start by the first problem because it will require a lot of time. So I will try to start by easy problems that will not take a lot of time so that we will be able to finish. Okay, so we need first to show the following relation. We need to show that the true strain is equal to ln times 1 plus the engineering strain. Okay, so always when we ask for such things, we should go back to the definition. Okay, by definition, what is the true strain? The true strain is ln L over L0. And if we want to relate it to the engineering strain, we should find a relation between L over L0 and the engineering strain. This is why we go back to the definition of the engineering strain. The engineering strain is defined as L minus L0 over L0. Okay, so if we rearrange our terms, we can say that E, which is the engineering strain, is L over L0 minus 1. So if we take 1 to the other side, we get that 1 plus the engineering strain is equal to L over L0. So by simply replacing L over L0 by 1 plus the engineering strain, we can get the relation between the true strain and the engineering strain, which is that the true strain is ln of 1 plus the engineering strain. Okay? Now, another problem. In a tensile test, a tensile specimen is elongated to twice its original length. Determine the engineering strain and true strain for this test. Then, if the metal has been strained in compression, determine the final compressed length of the specimen such that first, the engineering strain is equal to the same value as in tension. It will be negative value because of compression. And B, the true strain would be equal to the same value as in tension. Again, it will be negative value because of compression. Note that the answer to part A will be an impossible result, and we will see why. And determine the true strain is therefore a better measure of strain during plastic deformation. Okay, so let us start from zero. So first, they said that a tensile specimen is elongated to twice of its original length. So we can write that L final is equal to 2 times L0. Okay? And then, if the metal has been strained in compression, determine the final compressed length of the specimen such that, first, the engineering strain is equal to the same value as in tension. So first, we should find what is the value of the engineering strain. By definition, the engineering strain E is given by the formula L final minus L0 over L0. Okay, so what we have here, we have first, the final length is 2 times L0. So we have 2L0 minus L0 over L0. Okay, so we obtain that the corresponding value is 2 minus 1 over 1 equal to 1. Okay, so this is the value of the engineering strain, and the value of the true strain, so epsilon true, is equal to ln of 2L0 over L0, which will be equal to ln of 2. And as you can see, in case of tensile test, the true strain is smaller than the engineering strain. Okay, so it's ln of 2. So you get an engineering strain equal to 1 and a true strain equal to 0.69. Now, what they are asking for, they are asking that in case I do the compression test instead of the tensile test, but I obtain the same value of engineering strain, but of course in the negative sign, because you know that in compression, engineering strain is negative, okay, and also true strain is negative. So if we apply this, okay, to have E equal -1, if we write the relation, what is E? What is the value of E? Okay, the value of E is, in case of compression, is the final height, okay, minus the initial height h0, okay, over h0. So here the condition to have it equal to -1, the condition is this will give you, if you solve it, it will give you that h should be equal to 0, which is impossible. You know, I cannot compress a specimen until reaching a value of 0. Okay, but if I want to calculate if I use the true strain value, okay, in case of using the true strain value and the true strain definition, the true strain is equal to minus ln of, so it is ln of h over h0, okay, and since I have the numerical value, which is equal to minus 0.693, I can calculate the corresponding value of h, and I will get that h is equal to 0.5. Therefore, I deduce the ratio is equal to 0.5. Therefore, I deduce that L final is equal to 0.5 L0. What they want to say here, okay, is that the true strain will give a more logical result than the engineering strain, okay, because it will actually give a value that is relative to the actual area of the specimen, okay. So this is why we can deduce that true strain is a better measure of strain during a plastic deformation than engineering strain. Any question on this? Okay, another problem. So, yes, let us do the problem about Brinell hardness because it's a short problem. In a Brinell hardness test, a 1,500 kilogram load is pressed into a specimen using a 10 millimeter diameter hardened steel bore. The resulting indentation has a diameter of 3.2 millimeter. First, determine the Brinell hardness number for the metal. And second, if the specimen is steel, estimate the tensile strength of the steel. So here, what we should do, we go to our formula sheet. If you remember, we said that from the formula sheet, we have a relation between the Brinell hardness, the force applied, and the diameters of indentation of the bore. And we said that all we have to do is to respect units. So we should use F in kilogram, pay attention, not in Newton, and the diameters in millimeter. So if we just replace by the corresponding values with good units, we can get the value of the Brinell hardness. And we have seen that the tensile strength can be estimated from the Brinell hardness through the following relation. Tensile strength equal to 3.45 times Brinell hardness. And as you can see here, you can get the result, and the unit of the result will be in megapascal. So just for such a problem, pay attention for units. It's a direct application of a formula. So from it, you can get the hardness, and from the hardness, you can get the tensile.